Okay, so this is the second half of the concrete lecture. It's not a long lecture, so we'll go through how concrete is designed. Now, the design of concrete is simultaneously very complex and very, very simple. There's a lot of things that look very confusing about concrete design that are really just engineers simplifying, making assumptions about the simplification of the behavior. All that to say, I feel like that is way beyond what should be expected of you guys for this course with the amount of time we have to talk about it. So what I'm going to focus on is the really interesting part of concrete and the thing you need to understand before you can even start design on concrete. And that's the fact that it's composite. Because composite is a really cool thing. So before we can even talk about composite, we have to get an understanding of load sharing. So how do elements share loads? Then we'll talk about how maybe if we had two different materials, how could we talk about them as if they were the same material? Maybe that would make our life a little bit easier for calculations. Then we'll talk about what composite action means, and we'll look at some composite materials in the industry. And then we'll do a very brief overview of what concrete columns and beams look like and what goes into the design process. But there's actually very little math in the concrete design that you guys are going to do. We're going to be focusing on kind of the load sharing and composite action portion of the communication today. So load sharing. Load sharing is when two elements or materials are arranged so that they mutually support the load they are said to be sharing. When two elements or materials are arranged so that they mutually support load, they are said to be sharing the load. I'm missing a comma in there, I believe. The proportion of load that each resists is proportional to the stiffness of that element or material. Load will follow the path of greatest resistance. So that's a lot to try to explain something you already intuitively know. If you have two things side by side, the load is going to go, and you stand on both of them, the load is going to go to the stiffer element, or more of the load is going to go to the stiffer element. What we're saying is that if multiple elements support the same load, they share it based on stiffness. So the load likes the path with the most resistance. And we'll look at a few examples of what I mean to help you understand this intuitively. Now, stiffness is made up of two things, or can be made up with a relative stiffness of things can be made up of two components. There's the material stiffness, and then there's the amount of material that you have. Because a wood column that's this big and a wood column that's that big, even though they're the exact same material, this one's stiffer than this one because there's more of the material. So there's the material stiffness, and then there's the amount of material. Both contribute to the stiffness. So the area contributes to it, and the material stiffness contributes to it. Remember, we talk about that as E, or the modulus of elasticity. So area, A, and E, modulus of elasticity, are what help us determine the relative stiffness of two separate objects. So just as a thought exercise, if you stood on top of a column that was a steel rod wrapped in Play-Doh, which one do you think is going to take the majority of the load? Well, you know that the steel rod is going to take almost all of the load. Now, I've drawn this quite tall, which means we know it would buckle. Let's imagine it's a short little thing. You know that the majority of the load is going to go into the steel rod. The Play-Doh is going to deflect some, leaving the steel rod as the stiffer element. But technically they're moving together. It's just that the Play-Doh moves so easily that it offers up very little resistance. So this one's pretty obvious. We can look at this and we know the steel rod's going to carry all the load. What if that steel rod was wrapped in wood? Well, we know steel is a lot stiffer as a material than wood. Remember, E is 200,000 for steel, and we saw for wood it varied from around 6,000 to 11,000. So a much less stiff material. But there's way more wood here than there is steel. So it's not obvious to me which one is going to carry the majority of the load. We know there will be a sharing of load there, but we don't know how much each element is going to take. And that's important if we're trying to design each of those materials, because the amount of load that the steel carries, or the factored load on the steel, has to be less than the reduced capacity of the steel. And the factored load that the wood supports needs to be less than the reduced capacity of that amount of wood. So let's talk about an object. How would a concrete and steel column share load? Okay, so to share the load at all, they need to be squashing together. So if we're putting something on it and we're pushing down, and we've got even distribution over the top, they have to be moving together. Well, we know that movement can be talked about as a very specific thing, and we call that thing strain. Remember, that's the amount of movement we have, or the change in movement relative to the original length. So if they're both moving together, these two different materials, we could say that they're experiencing the same strain, because the relative movement to the original size is the same. So let's remember our basic formulas. Stress equals force divided by area, or force equals stress times area. That's the same equation, just written two different ways. Oh, look at that. My mouse is doing that ridiculous thing where it gets very small, even though it's very big on my screen. Sorry guys, let me make my mouse bigger for you, because it's going to be handy in this particular thing. My settings have disappeared from here. Okay, let's just find my mouse settings. Sorry team, I just want to make sure you can see my size easily. So for me, this is a much larger mouse that I'm seeing right now. It got bigger, but you guys don't see it. It's gigantic for me now, and then all of a sudden, it's gigantic for you too. Let's make it a funner color today. Okay, sorry about that, team. Okay, so here we are. We're back. You can see my gigantic mouse now. That it did that all last year, and then didn't do it at all this year, and then all of a sudden right now it's gone back to doing that. So I don't quite know what's going on. Okay. So we have our equation that we already know. So this is the same equation. Stress equals force divided by area, or force equals stress times area. We know that strain equals the change in length divided by the original length. And we know E, our modulus of elasticity, is stress divided by strain. We can rewrite that as stress equals modulus of elasticity times strain. That is just the same equation. Let's start substituting some things into each other. If I take this equation here, so force equals stress times area. So force equals stress times area. Instead of stress, let's use E times strain. So F equals EA strain, where E and A are for a particular material. If for each material they're moving together, we know the strain has to be the same. So the force in the steel and the E for the steel and the area for steel, that strain has to be the same as the force for the concrete, the E for the concrete, and the area for the concrete, because they are moving together. So for each material, the force in the steel equals EA steel times the strain, and for the force in the concrete, EA concrete times the strain. But the strain is the same for both. Okay, the total load is the load in the steel plus the load in the concrete. We only have a certain amount of load and it's shared out between the two. And we want to figure out what that division is. Well, we know the load in the steel was EA steel times the strain, and the load in the concrete was EA concrete times the strain. And the strain is the same for both. If the strain's the same for both, let's just kind of bring it outside of that equation. So the force, the total force, equals the strain times the sum of EA steel and EA concrete, or the sum of all of the relative stiffnesses. Remember, EA for each material is the relative stiffness of that material. Some component of it is based on the material. Some component of it is based on the amount of the material. So the sum of EA is the axial stiffness of the combined system, or the whole system. So if we rearrange this, the strain is the total force divided by the sum of the EAs. We can plug this back into our steel and concrete breakout, and we can see that the force in the steel is the total force of the EA steel divided by the sum of all the EAs. Or basically, this is the ratio of stiffness for the steel times the total force, and this is the ratio of the stiffness for the concrete times the total force. So these are the percentages of load that go to each component. I know, that's a pain in the butt. Why don't we do an example? So we'll break one down and we'll take a look at this steel HSS filled up with concrete. All right. That's a horrible shadow, isn't it? Let's see if that's a little better. All right. My trusty pens. And make me gigantic. All right, team, here we go. We want to know what percentage of the load goes to the steel and what percentage of the load goes to the concrete. Let's draw it out here. We have our HSS, and then it's filled with concrete. Do a gut check. What do you think? Well, they told us that the E of the concrete is 30,000 MPa, and we know the E for the steel is 200,000 MPa. So that makes the steel component stiffer. But look at the amount of concrete relative to the steel. I didn't hatch this very well. So it's not obvious to me which one's going to take more of the load. This is why I wanted to talk about one where you intuitively knew the answer before we did a calculation. So we talked about the Play-Doh and the steel. But this one's not obvious to me. I'm guessing it's going to be about 50-50. But again, this is just a guess for me. Prediction that the F in the steel is going to be about equal to the F in the concrete. I don't think it's obvious to me that one is gigantically stiffer than the other. So I think that's probably a good guess, but I don't know how much. So we know that the key to all of this, we know they're moving together, so the strain is going to be the same, but we know that E and A are very, very important for all of these. So let's talk about the steel. We know that the E for steel is 200,000 MPa. That's a thing you should know by now. The A of the steel, well, we can go look that up. Remember, we have all of those steel tables, and we have properties for this HSS 152 by 152 by 9.5. They told us this. That's the member that they told us we'd be using. So the area of the steel, if I go look that up, I will see that the area of that particular member is 5,210 millimeters squared. And I know that this EAS, or the E of the steel and the area of the steel is going to be kind of important. So why don't I just calculate that right now? I've got my 200,000 times my 5,210. Looks like it's going to be a big number. My calculator just does not like me lately. See, it wants this bright light, but that makes it impossible to see. Oh, that's not so, it's a bit glary, isn't it? My calculator certainly likes that better. Times 5,210. All right, 1, 2, 3, 1, 2, 3, 1, 2, 3. 1.042 times 10 to the 9 newtons. So this was newtons per millimeter squared, and this is millimeters squared, so we're left with newtons. That's too bright, isn't it? Maybe that's all right. Oh, now we can't see a gosh darn thing on my calculator. My calculator is just shot, Dave. The solar panels aren't working on it very well. Okay.
You want to try mine?
I think I did, and yours isn't doing it either. Oh yeah, no, yours is a heck of a lot better. So I think I probably just need a new calculator. Okay, concrete. The E of the concrete, they gave it to us in the question. So E of concrete is dependent or related to its strength. I would not expect you to know what that is. I would always give that to you. Maybe say in a question, and maybe say in the assignment, one of the questions is, what's the E of the concrete? And it is literally in the question. You can just go write in whatever is in the question. They told us for this one, the E is 30,000 MPa. Well, let's figure out what the area of the concrete is. So the area of the concrete is this bit in here. We know that this is 152, and this is 152, and that dimension is 9.5. So let's figure out what amount of concrete we have there. I'm not going to worry about the rounded edge too much. That's maybe refining it a little too much. But we've got 152 minus 9.5 times 2, so this dimension right here, times 152 minus 9.5 times 2, or this dimension right here. So let's calculate that. We've got 152 minus 9.5 times 2, so 133 times 133, we get 17,689 millimeters squared. So the EA of the concrete is our 30,000 MPa times 17,689 millimeters squared. We can multiply that by our 30,000, and we get 1, 2, 3, 4, 5, 6, 7, 8, 9. 0.53067 times 10 to the 9 newtons. I could have rounded that. I'm just trying to keep this kind of pretty tight for right now. We also know that it's important to know the sum of all our EAs, or the total stiffness. So this is the stiffness of the steel, this is the stiffness of the concrete, and we want to know the stiffness of the entire system. Well, that is EA steel plus EA concrete, or 1.042 times 10 to the 9, maybe I'll just keep 3 significant digits here, plus 0.531 times 10 to the 9 equals, let's do 1.042 plus 0.531, 1.573 times 10 to the 9 newtons. So that's the stiffness of the entire system. So this is how stiff the whole system is. This is how stiff the steel is. and this is how stiff the concrete is. So the proportion of this stiffness that goes to the steel is how much load the steel takes, and the proportion of this stiffness, of the total stiffness that goes to the concrete, tells us how much load the concrete takes. So we can now find the load that would go on the steel. It is the percentage of the load times the EA of the steel divided by the EA of the system, or the sum of the EAs. They haven't told us what the actual load is on this. We don't actually know what the load is. So we'll just keep the load as F times the EA of steel is 1.042 times 10 to the 9 divided by the sum of the stiffness, or the entire stiffness of the system. We get 1.42 divided by 1.573. We get that 0.662 of the load goes to, of the total load goes to steel. Or what we're saying is the steel takes 66.2% of the load. That's pretty darn close to 50-50. I mean, it's not. It's greater than 50%, but it's not, some unreasonable amount. It's not 99% of the load. So it looks like our prediction was not the best, but certainly in the realm of verifying our calculation. Let's look at the force in the concrete. Now, I know some of you are like, oh, it's just what's ever left from 1. We could do that by doing 1 minus 0.662. We can. Let's just do it this way. The total force times the EA of the concrete divided by the total stiffness of the system equals F times our 0.531 times 10 to the 9 divided by 1.573 times 10 to the 9 equals, so 0.531 divided by 1.573 is 0.338 F. Or the concrete takes 33.8% of the load. So we just were able to figure out how much of the load goes to each element. If this was carrying 100 kilonewtons, we'd know the steel has 66.2 kilonewtons on it, and the concrete has 33.8 kilonewtons on it, meaning that we could then check the capacity of the steel to see if it's strong enough to take its load, and the capacity of the concrete to see if it has the capacity to carry its load. Okay, so that's worked out here, so you can go through it at whatever rate you're comfortable with. So I have it written out here too. It looks like my exponents disappeared on this, but you know what that's supposed to be. Okay, so this is when we want to talk about these as disparate materials, because they are separate materials. Sometimes what's really handy for us is to actually pretend the materials are the same. So rather than say, this is the combined stiffness of the steel, and this is the combined stiffness of the concrete, depending on the material properties and the area of it, sometimes what we'll do is we'll talk about them as if they're the same material, because that can make some of our calculations a little bit easier. Let's see what I mean with that. So we know our strain equals our force divided by our stress times our EA. This is again just rearranging some of those equations we've already looked at. So any object of any material or combo of materials will act the same as long as stress EA is the same. So we could say that the total system was E of 1.571 and A was 1 millimeter squared. Or we could say it's the equivalent to a system that has a material of 1 MPa and 1.571 times 10 to the 9 millimeters squared. We could rewrite that system that we had in this way, just to help us process transforming one of the materials into the other. Now, I know this sounds confusing. I'm going to do an example for you. So what we do is we will then create something called N, or a multiplier, to transform one material into the other. So let's take a look at that same concrete column. Let's transform it. Let's transform our materials into each other. We're going to keep this handy because some of the stuff we want to see is in this. So we've been asked to take the HSS column that was filled with concrete and transform the steel into an equivalent column of concrete. So that's what we've been asked to do. So we had our HSS that's filled with concrete. And we knew that the area of our steel here, we've looked this up, was 5,210 millimeters squared. The E for steel is 200,000 MPa. And we know that the area of the concrete, we already calculated this, was 17,689 millimeters squared. And the E of the concrete they gave us in the question. All right. If we want to transform the steel into concrete, we want to transform the area of the steel. So we want to figure out what equivalent area we'd need of steel if our stiffness was the same as our concrete. So this is what the area is with this stiffness. What area would that be if we transformed the stiffness of the steel into concrete? So that's essentially what we're doing here. We're saying that the E of the steel divided by the E of the concrete times the A of the steel is us transforming the steel into concrete. Or 200,000 divided by 30,000 times 5,210 millimeters squared. Let's take this 200,000 divided by our 30,000 times 5,210, and we get that the area of steel we would need, or the area of our transformed section, would be 34,733 millimeters squared. So what we're saying is we knew that our combined system of steel for the modulus of elasticity in the area was stiffer than the concrete. If we said that that steel had the same material stiffness of the concrete, we can figure out how much area we'd need, or what the equivalent area would be. Remember, our steel system was the stiffer system, so it makes sense that it would have the bigger area. What we're saying here, well, let's look at this. Let's look at the total area now. So our area effective is the area of the concrete plus the area of the transformed section, or 17,689 plus 34,733. If we plug this into our calculator, we get 52,422 millimeters squared. So this HSS 152 by 152 by 9.5 filled with concrete is the same as I've probably drawn this too big, but it is the same as, this is our original bit of concrete, and then this is our transformed steel section. With an area of 52,422 millimeters squared and an E of 30,000 MPa. So we're saying that this system here with these properties is the same as this system here with these properties. So what we've essentially done is figured out what amount of concrete could replace that steel to do the same job as the steel was doing. And that's called a transformed section. And it's really, really handy when we talk about bending. Now, I'm mostly just touching on it because it's a really cool thing to know. I am not going to make you do any calculations on it, but you should know it exists. In fact, I think there maybe even is a question that says, what neat thing can you do to help talk about materials as a different material? But I'm not going to make you do the calculation. So, hot tip, that is definitely a question that you have this week. Okay, so that's all worked out here. Now, obviously, so here's one where I've actually drawn it to scale. I actually did that in CAD and actually drew it out to scale. So these are the same, effectively the same. So we're ignoring buckling in this. Obviously, if this was a column under compressive load, we don't have buckling happening in this. Oh, here's what I need to do. You missed me. Hi. Okay. So let's talk about composite now. What does composite mean? So here, let's twist it around. Okay. If two objects are combined so they support the load as one object, the system is said to be composite. In order for a system to be considered composite, the material must be bonded so that it won't slip relative to each other. What does this mean? All right. Let's take a look at some images in just a second. In axial loading, it's very, very easy to make this happen. But in bending, we need to make sure that the shear can transfer across the plane where the materials interface. So let's take a look at this. They can be two different materials, or they can be two pieces of the same material. So composite system versus non-composite, or sharing. For bending elements, longitudinal shear is critical. If there is no bond along the interface or the shear plane, the element will slip along that plane. So this is longitudinal shear is critical to make an element composite. Again, super handy quiz and exam question. Longitudinal shear is critical for composite action in bending. So if we don't glue two things together, it's like we have two small beams sharing the load. If we ensure that the two planes don't slip, it's like we have one big, deep beam. So let's take a look at an example here. So if we have this section right here, and maybe it's worth me doing this as a calculation. Yeah, I'll go through a calculation in just a second. So if we have two 140 by 140 timber beams spanning some distance, if we don't glue along that plane, they will both bend. They'll both bend and they'll both do work. They will share that load. Two beams are better than one. So two beams this side are fantastic. We've doubled the capacity of this system, which is great. So you can see our extreme fiber here and our extreme fiber here, which means our couple for this is that distance. Do you guys remember when we were calculating the shape property for bending? It was, for a rectangle specifically, it was BD squared divided by 6. So the D, or the depth of the member, had a huge impact on it. So here we have two members that are the same depth. Here, we've glued this plane together. So that can't slip relative to each other. This slippage can't happen right here. This means we've made one beam that's much, much deeper. Think of it this way, and if you took a phone book or a paperback book and bent it, all of the pages slipped together. It's a lot stronger than one single page of paper, for sure. Actually, look at this. I've got paper right here in my hand. They all slip relative to each other. And if it was a big enough book, you could actually see that those are slipping relative to each other when you bend them. Take a stack of paper, do it. You'll feel it happen. If I took the time to glue all of these together, I would have a much stiffer system, because instead of 10 paper thin things, I've got one object that's quite thick now. Let's take a look at what this means. Here's our maximum stress, the maximum stress at the extreme fiber we want to see. So let's find the shape properties A, S, and I. Remember, A is what we needed for shear and for axial loads. S was the shape property we used for bending. And I, or moment of inertia, was the shape property we used for deflection. So remember, all of those equations we looked at, everything we did had a shape property in the equation. And so the shape of our member was very important. And these were the three shape properties. The three shape properties we looked at. We've been up a very long time. Our kids woke up, which is why the recording is late, by the way, everyone. My kids woke up before me when I was going to record my lecture at 4 o'clock. So I didn't get to record it. I had to deal with very small children who were very, very cranky that they were awake. Okay, let's look at these members. And I really like this calculation because it's simple. It's very, very simple, but yet very, very effective at showing us what needs to happen here. Okay. All right, let's make my calculation screen big for you. Okay. Let's look at, we have this object that is 140 by 140 sitting on top of this object that is 140 by 140. There's no glue here. And then let's also look at this object where we've glued them together right along here. So we've done a great job at gluing this together. And so we're saying that we've effectively made this act as one big solid object. So this is 140, and this is 280. All right, let's look at the area that we have here. Remember, area was handy for axial loads and shear loads. We have 140 times 140 plus 140 times 140. Or 140 times 140 plus 140 times 140. We have an area of 39,200 millimeters squared. Let's come over here to this object. Let's take a look at our area. Area equals 140 times 280. 140 times 280. Oh, well, that's not very exciting. Our area is the exact same. If the shape property that we use in shear and axial loads is area, it looks like making it composite or taking the time to glue that together didn't do anything for us. So for axial loads, there's no real advantage to making it composite. For shear loads, there's no huge advantage for making it composite. So this was for axial and shear. Let's look at the bending shape property. The bending shape property is S. And if you guys remember, for a rectangle, S is BD squared divided by 6. So we have the S for these two is 140 times 140 squared divided by 6 plus 140 times 140 squared divided by 6. Let's take a look at what we get for S. 140 times 140 squared divided by 6 plus 140 times 140 squared divided by 6. Okay, we get 0.915 times 10 to the 6 millimeters cubed. Okay, let's take a look what S is for this object. S is BD squared divided by 6. Well, we have a B of 140 times our 280 squared divided by 6. Let's see what S we get now. 140 times 280 squared divided by 6. We get 1.83 times 10 to the 6 millimeters cubed. Look at this. It's double. We've doubled our bending capacity simply by gluing these two objects together. Let's take a look at deflection, or I. Remember, the modulus of elasticity for an object was BD, or for a rectangle, was BD cubed divided by 12. So let's just B times D. This is BD squared divided by 6. And this is BD cubed divided by 12. So I think you can see where this is going. Let's take a look. We've got I equals 140 times 140 cubed divided by 12 plus 140 times 140 cubed divided by 12. I equals 140 times 140 cubed divided by 12 times 2. We've got 1, 2, 3, 4, 5, 6. We've got 64 times 10 to the 6 millimeters to the 4th. Let's take a look at this one over here. I equals 140 times 280 cubed divided by 12. 140 times 280 cubed divided by 12. We get 256 times 10 to the 6 millimeters to the 4th. That is 4 times as stiff. So simply by gluing this together, we have quadrupled the stiffness of this. So same amount of material in both of these. So we didn't change the amount of material. All we did was make sure these two small objects were glued together, and we quadrupled our stiffness of our system. So that's incredible. Just by ensuring this shear plane is glued together, we have made sure we have doubled our bending capacity and quadrupled our deflection capacity. That is the huge advantage of composite action. So this is why we would bother to make something composite. So let's take a look at some composite systems, because there's lots of composite systems that we use all the time. So our concrete on metal deck is a composite system. Remember, concrete has effectively zero tension capacity. Our deck is bending. Concrete is great in compression, so we have the concrete at the top where it's in compression, and at the bottom, steel is fabulous in tension. So look at this. We've got our concrete on the top and our steel at the bottom. This one's extra fantastic because concrete needs formwork. And look at this. We might as well use the metal that we have as our formwork and just leave it in place and let it do work for us. So these two things acting compositely have a very, very effective system. How do we make it composite? Well, remember I said way back when, this deck is the same as our normal deck. It's just got these little flutes punched into it. Those are grabbing onto the concrete. So as it bends, those are wedged into the concrete, basically forcing the two things to be composite. We can actually make concrete on metal deck composite to our beams. So if this is our steel beam, we can use some amount of that deck system that's already composite in with our steel beam. If we put these lugs in to force the composite deck to be composite with our steel beam, the composite deck will take the compression in bending, and the steel will take the tension in bending, but we've increased the effective depth of our system. Instead of just the depth of our beam, we've got the bottom of our beam all the way to the top of our concrete. So we've improved that system. Now, here in Toronto, or in most applications that I'm designing in, that doesn't offer a lot of advantage to us because we're often governed by vibration criteria, and this doesn't improve our vibration criteria, which means we have to end up upsizing the beam, and once we've upsized the beam, it tends to work for the load, so why would we go through the added cost of adding the shear lugs if we don't need to? If it doesn't improve anything, or we've already met all of the criteria that we need to meet by just having this bigger beam that we needed anyway for vibration. That's why this isn't used all the time. It's selectively used for specific applications. Remember when we were talking about our wood floor systems, and I said if you tried to stand on just this joist without a plywood deck, all of your load would go to this joist. Once you put that deck in, it tries to pull the deck down with it, which means this deck engages these just a little bit. These are often glued together and nailed, and there's criteria on how these come together. If all of that is done, we get essentially to say that we have some top flange of our plywood working with us. So a class 2 system of joists or studs is a composite system. Our wood elements for I-joists actually have two composite systems in them. The OSB, which is a bunch of pieces of wood mixed up and all glued together, that's composite. And then we have our top flange and our bottom flange glued to our web. That glue joint is transferring our shear along a longitudinal plane, making our system composite. So the top chord and bottom chord are doing all the work for bending, but yet our web is doing all our work for shear. SIP panels. So these are wood top plate, wood bottom plate with basically insulation glued in between there. What makes this composite is that this plywood is glued to the insulation and the bottom plywood is glued to the insulation. We can get into really advanced composite systems. I talked about under the gardener and how the concrete spalling off can be a bit of a problem, but how impressive it is that the concrete has lasted as long as it has. What we can do is take Kevlar or carbon fiber or glass materials in these sheets and glue them to the underside of the concrete in our bending application. So they're fantastic in tension, not great in compression, but fantastic in tension, and we can glue them onto the bottom to preserve that bottom. These are so impressively strong, it begs the question, why don't we do that right off the bat? They're also so impressively expensive, so we don't do it unless we have to, usually as rehabilitation, for example. So this is a column that's having the outside spall off, and we wrap it in the Kevlar or the fiber system to contain the concrete. Okay, today's star of composite action is our concrete reinforcing. Let's now talk a little bit about what happens for concrete elements in design. We're not going to do the design. I think that's way too much for you guys. We're just going to talk about how the whole process works. So right off the bat, we're going to go through this a little bit in a few minutes, but the columns, concrete columns, the concrete and the steel both take the compressive load. In a beam, the concrete does all of the compression work and the steel does all of the tension work. Sometimes we'll have the steel do some of the compressive work as well, but not all the time. We don't usually start there in our calculations. Shear is taken by the concrete, or sometimes we'll count on these reinforcing stirrups as well. So we'll take a look at that in a minute. These are a few of the slides that I showed you in the first part of the lecture that I said showed up in both lectures. So we've already talked about the properties of our reinforcing. And we've talked about some of these aspects of the reinforcing. And we talked about some of the material strengths for concrete. And we looked at the stress strain curves of both of these. So let's talk about what happens with a concrete column in compression. So the concrete and the steel share the load based on stiffness. Remember, we talked about that at the beginning of this lecture. Load sharing. It's based on the area of the material and the material stiffness, contributing to the overall stiffness of the system. We've got small amounts of area of steel, but they're very, very stiff. We've got a large amount of concrete with a much less stiff material. So the steel has two roles in compression. The longitudinal steel carries some of the load, and we need to design it for its capacity to carry that load. We also put ties around that steel to stop the concrete from bursting prior to the concrete reaching its full corrosive strength. Remember how we said we're going to ignore the fact that things tend to bulge out a little bit when we put compression on it? Well, the fact remains that it does bulge out, and so the ties we put in there are to help deal with that tendency for the concrete to bulge out. The reason why reinforced concrete columns are so freaking neat is that the column is actually composite. The strain must be the same for both the steel and the concrete. The steel is much stiffer than the concrete, so the steel stress will be much higher than the concrete stress. They have the same strain, but they have different modulus of elasticity, which means the stresses must be different. The steel stress is much, much higher, but the steel has the capacity to take a higher stress. The steel will hit its yield stress prior to the concrete reaching its F prime C. The steel then yields, but the steel will continue to yield. Remember, we like yielding for steel. It shows ductility until the concrete can reach its total full capacity. So we can actually take total advantage of both materials all the way to their limit. We can make use of the full Fy of the steel and the full F prime C of the concrete, even though the steel might be starting to yield. That's a pretty cool thing. So what do concrete columns look like? Okay, so I just went online and found some images of them to show you how you can lay out the reinforcing. So the blue line is the outline of the concrete, and the red is the reinforcing, the ties, and the pink is the longitudinal reinforcing, or the thing that would be carrying some of the compressive load. So here it is from a side view, and here is a cross section of the column. So you can see that what is key is wrapping all of those bars in some way. We want to contain those bars within these ties. And there's all kinds of different ways you can do this layout. This is a pretty common layout for our concrete and our ties. Here are some views of some round ones. Again, you can see we are containing it in these ties. Sometimes these ties will be spiral. I have never worked with spiral ties. Have you ever worked with spiral ties on a project?
No.
No.
They're used for high seismic typically, but they're using them in Ottawa on the Peter Point Bridge.
In the caissons or in the elements?
In the piers.
In the
Probably
piers.
the caissons too.
So Dave just said that the spiral ties, it's a little bit harder because they're continuous now, right? You've got to keep going with them. This is nice that you come on site with this thing and you kind of bend it around and tie it off. So they tend to like this because they can assemble it a little bit easier. But those spiral ties are good for high seismic zone. I'm guessing it's the way it deals with the ductility and how it spreads out the load through the element. So Ottawa is a surprisingly high seismic zone. And look, once we accept that if you can build the formwork for the concrete, you can do whatever you want. You just have to make sure you tie it together or contain that reinforcing steel. So here are just some really cool shapes of concrete columns. I've done all of these ones. I've done this. I personally haven't done this one, but actually that's not true. I've done one even more complex than this for Shim Sutcliffe on Integral House. They're peanut-shaped columns. So they had...
On Sisters.
Yeah, it was Sisters, right? Not Integral House. They did all the steel ones in Integral and Sisters. And they crossed those ties over the peanuts, right?
I think so, yeah.
So my memory is they were almost figure-8 ties. So for that, they had peanut-shaped concrete columns. And so you can see here, they had to contain all of that, but also tie the two halves of the peanuts together. So I didn't do the final design for that, but my canopy then had elements that were cored down in between that. All right, a concrete beam in bending. So this is what a typical concrete beam looks like. Here's the outline of our concrete. And remember, this might be in the depth of the slab. So our slab might be there as well. These are our bottom pieces of reinforcing. Remember, most of the time, things are bending like this. So we need our steel to do the tension work because concrete has zero capacity in tension. So bending, compression at the top, tension at the bottom. We put our steel in to do the tension work. The concrete is doing all the work for compression at the top. These ties are doing the job of our shear reinforcing. Remember, the cracks tended to propagate in a diagonal in shear, and so we want these to cross the path of the propagation or of that crack. So what are these two pieces of reinforcing doing? Well, most of the time, they're holding the ties up. Sometimes we actually use them in our calculation. There are conditions where our beams have reverse bending. In those conditions, we need steel at the top to also do the job of tension steel for reverse bending. So let's take a look. The compression zone, the concrete does the work. Most of the time, that's the top portion. The tension zone, the steel does the work. So let's take a look. We have our concrete cracks down here because it has zero capacity in tension. These cracks propagate. The steel is right here, and our concrete is up here doing all the work of the compression. In our cross section, here's the zone of concrete that's in compression. Here's our steel and tension. Ooh, what if, to make this easier, we pretended those 3 steel bars were some equivalent amount of concrete? Look at this. They transformed the section. This is the same as saying we've got this much concrete up here and this much concrete down here. This is the equivalent amount of concrete at the stiffness of this concrete to do the work of this steel at the stiffness of steel. So here is our strain diagram. Here is our stress diagram. I'm going to show you another one in just a second that's a little bit cleaner than this. This is how we simplify the stress profile of a concrete beam in bending. This makes a fantastic exam or quiz question. If this is our cross-sectional area of our beam in bending, our concrete is taking the compression, or this is our compression block right here, and so that is the compressive force of our concrete, or our capacity of our concrete, and our steel is right here doing all the tension work. There is our couple distance right there. So this is a great exam question. A concrete beam in shear. We say that there's a whole concrete blob here that can take shear, which is great, until it starts to crack, and then we want our steel in there. So what we'll often do is we'll do the calculation and see if the beam works in shear without even accounting for our steel. And then if that doesn't work, we'll take into account our steel shear reinforcing stirrups spaced along the beam. So here you can see what it looks like where we've got our ties along the length of our beam. So often we would say that these are, 10s at 300. So every 12 inches we have a tie that looks like this. So there's a lot of steel hidden inside our concrete beams. This is a simplified diagram of what's happening here. Here are our cracks. And you can imagine it's like a stress acting along a truss. Really, this is what's happening in the load here. And so we put these stirrups here to prevent these cracks from propagating. So what do our concrete beams look like in profile? Well, this is the normal one. This is what we do right here. What if, since we're probably in the depth of our slab anyway, we took a little more of the slab? Because remember, compression is our concrete job. Maybe we need a little more concrete zone in our compression. We could make a concrete T-beam. We can do really large concrete beams as well. But remember, as they start to get too large, their own self-weight starts to be the detriment to them. So that's it. That's all we had to cover for concrete. So here are your study tips. Load follows the stiffest path. Load sharing of 2 members is additive. Composite action of 2 members is like having 1 large member. If we glue that longitudinal shear plane together, we have 1 large member. So the longitudinal shear is required for composite action in bending. The compression for concrete is taken by steel in the concrete. The bending, the concrete takes the compression, the steel takes the tension, and we use both for the shear. So those two sound like they might be questions on possibly the quiz, and you have the answers right here and throughout the lecture. So the assignment this week is a little bit long. Go through it. Some of it is in stages, but there are lots of easy points embedded in those questions. So some of them are directly from the question. Some of them are not sequential. I've tried to indicate which ones are sequential. To make life easier, I did not make it a number input. I made it so that it was a multiple choice question, which means if you're off by a small rounding error, you can see which one's the right answer fairly easily. But if you do something using the wrong numbers, a wrong answer might be there that looks like your wrong answer. So just be very careful. This is going to be posted in time that you can listen to it possibly during the first half of the tutorial if you needed to, so that you can still have questions ready to ask during your tutorial. So next week is the last week, and I'll talk to you next week.